in high gear. Let's start off with our first presenter, which I believe is going to be Boss Technologies from NASA. So again, we're going to give you 8 minutes to present your presentation, followed by about 6 to 7 minutes of Q&A. I'll give you about a minute notice before the 8 minutes is up. And
logo.
Now, is this technology that exists that's available to businesses right at this point in time? That is wonderful. So I'll let you introduce yourself, a little bit about the technology, and I need for you to stand in the middle.
Good afternoon, everyone. My name is Patrick Chan. I'm an optics engineer at NASA. Today it's a privilege for me to present the FOSS technology, which stands for Fiber Optic Sensing System technology. Usually I give this talk as for technical conferences. A 15-minute talk, I usually do 13-minute and 2-minute question, but this is an 8-minute tech rodeo, so I'm going to go really quick. And if you have any questions, just don't hesitate to ask me. So basically, what we do is we use fiber optics for sensing. Fiber optics is what you use for telecommunication, but what we use is for sensing technology, so we can sense environmental perturbations such as strain, temperature, and other purposes. So here's the slide that we like to use. So why do we use fiber optic sensor as opposed to traditional strain gauge on the aerospace industry? This is kind of like a Sesame Street slide. So one of these things is not like the other. So first thing is heavy. So traditional strain gauge is, you can see there's bundles of wires that traditionally you need 3 wires to get 1 strain gauge. So if you add up it's heavy. So here's a close-up of it. You can see there's 3 strain gauge here that industry call a rosette. So it will do the X, Y, and 45 degrees angle. And you see the accompanying cable. So if you want to have a lot of sensor, it's really cumbersome. And this is the actual installation on one of the facilities in Colorado. The left is the strain gauge and the temperature probes. So you can see if you have hundreds of points, it is really cumbersome and it will drive you down. So it's really hard to implement it. So here comes the fiber optics. You can see just a strand of hair. It's light, it's small, it's easy, and there's hundreds of sensors you can put into one piece of fiber. So why do we use fiber optics? Is immune to EMF weight, so you can put it onto a lot of structure. It's light, it's easy. You can put hundreds of sensors into one fiber. So here you can see, it's kind of hard to see. You can this test panel, we have around 10 sensors here. So and then you can see a accompanying cable. But on the fiber optics, we can do the whole thing with around 60 sensors, each of them around ½ inch for each of the sensor. So you can see the tremendous weight saving versus traditional strain gauges. So the fiber that we have is a special fiber. It's called fiber Bragg gratings. It basically has a mirror inside the core of the fiber, and then we notice for whatever environmental perturbation, like an accordion. So if you stretch it one direction, it will change the wavelength. So we actually have laser that monitor the change of wavelength for all these fiber. And this is the NASA patented grating modulation method, which we call OFDR, optical frequency domain reflectometry. And so we have a sweeping laser that actually sends light throughout the length of the fiber, and then the reflected light, we collect them, and then we do some signal processing to it to get all the strain, to get all the environmental perturbation data. So layman's term, this is basically tuning a radio station. You have multiple frequency, and then you have particular radio. This is the interrogation system that we have, and then we tune it to a particular sensor that we want. So let me skip all these. So why do we want to use fiber sensor? This is the background. The motivation is for drones, specifically the Helios mishap. So if the flying structure, like a flying wing, if it have too much strain, then you don't know what happened to it. So if we have real-time shape sensing, string sensing. We can actually alert the pilot, okay, so we need to fly higher to avoid turbulence, so we can actually save this vehicle. So this slide is around Armstrong's role in fiber optic sensing technology. We developed the technology with Langley back in the mid-90s, and it was a laboratory system. You press a button, you wait 30 seconds, you got some data back. So throughout this 15 years innovation, we miniaturized the system, and then we speed up the algorithm, so now we can have up to 150 samples per second. And then the system is actually shrunk from a laboratory system to an under 10-pound interrogator system that we actually put it onto our own UAVs. So the field of application is actually, you can think about it, we can actually sense it. So strain, we can do shape, we can do cryogenic liquid level, we can do magnetic field, we can embed the strain into composite structure. So because of time, I'm just going to do a couple of examples. So this is the Project Icana that is a Predator 2 plane that we have. So we put fiber onto the wing of a vehicle, and during flight, we have a couple of patents. So by the strain of the shape of the airplane, we kind of know we can actually back out from the strain. We can back out the shape of the wing deflection. So here's an example. So you can see on the top, this is real-time data of the strain across the Icana wingtip, and then you can actually see the wingtip deflection real-time, the left wing and the right wing. This is real flight data. So we've been flying on vehicles since 2009. We've flown on the Predator, we've flown on the Global Observer, and we flew onto our own G3 aircraft. This is another innovation beyond aerospace industry. This is on the space side of the house. So one of the things that we want to measure is the cryogenic liquid level temperature. So for liquid oxygen, liquid hydrogen, for propellants, it's really hard to distinguish the liquid phase and the gaseous phase inside a coolant, because the gaseous phase will get really cold, so it's hard to distinguish the level. The traditional way for industry to do this is called something called cryo rake. It's similar to a strain gauge. So if you have a 40-foot height, a container, so you can imagine if you want to measure every half inch on using cryo rake, the cabling actually adds up. So we have an approach, we have a patent that use fiber optic technology to get these liquid level. So the result is the cryo-fast sensor can discern liquid hydrogen level to approximately a quarter inch in every case. So it's a good technology. So I know that my time is up. So in summary, that NASA has developed a lot of fiber optic string sensing technology, from laboratory to licensing to real-time use. There's aerospace application and beyond, and we're all already working with other sector, the medical industry, to use the fiber optic sensing technology beyond aerospace. There's a lot of emerging field that I would like to, if you guys have questions, I can answer them. So in summary, here's the FOX group. Thank you all. Thank you for your attention.